Hi everyone, welcome to Calc with Cola. So today we're going to talk about the first part of Unit 10, the different series tests, and we're going to go through all the different series tests that you need to know for the AP exam. So if you look right here, you can see all the different tests: the geometric series test, the nth term test for divergence, the integral test for convergence, the harmonic series and piece series, the alternating series test, the limit comparison test. I don't teach the direct comparison tests, but it's very, very similar. The ratio test and absolutely versus conditionally convergent. Okay, so let's look at the first test. So we have the geometric series test, and we're going to use it when we have a geometric series. So the series has to look like this. We have a r to the n minus 1, and sometimes we have a r to the n. So sometimes we might have a r to the n as well, and it would just shift the index, and it would start with n equals 0 to infinity. Now here are the conditions of the test. We converge if the absolute value of r is less than 1, and we diverge if the absolute value of r is greater than or equal to 1. If we converge, we can find the sum of the series. So if we converge, we can find the sum. A stands for the first term in the series, and then r is the common ratio. Okay? So we're going to look at two examples that I have here. So for the first example, this looks just like a geometric series, a r to the n minus 1. R is equal to 1/2. The absolute value of r is less than 1. So we're going to converge by the geometric series test. So if that's me showing my work, I showed the conditions that the absolute value of r has to be less than 1. And then I'm going to say we converge by the geometric series test. So now say they want us to find the sum. Now here's my suggestion, because I know we can tell that a is equal to 3, but if I were you, I would start by plugging in values for n, just to make sure, especially if you're not sure what r is or what a is. So watch. So when n is equal to 1, if I replace this n with 1, the first term is going to be 3. If I replace n with 2, the next term is going to be plus 3/2. If I replace n with 3, the next term is going to be 3/4, and so forth. So yes, the first term is 3, and the ratio is 1/2. So the sum is a over 1 minus r. If you do this out, that's 3 over 1/2, which is going to be 6. All right, let's look at this next one. So this is a geometric series. We have a r to the n minus 1. R is equal to 4/3. So the absolute value of r is greater than or equal to 1. So we are going to diverge by the geometric series test. Okay? If we diverge, we're done. We do not converge. Obviously, there's no sum. We don't converge. All right, next test, nth term test. So this is called the nth term test for divergence, and it only tests for divergence. That is super, super important. So this does, I'm going to say only test. I already wrote that. Whoopsie. I'm going to write does not test for convergence. And this is a great test to use if you can easily take the limit of the series. So you're going to use it if you can look at the series and say, oh, I can figure out the limit as n approaches infinity. And we diverge if the limit does not equal 0. So as long as we get a number, we're going to diverge. Seems kind of weird, but that's how the test works. So let's look at this first one. So we're gonna want to show it. So let's take the limit as n approaches infinity of the series. We get 3/2, which is not equal to 0. We're going to want to say that. So we're going to say diverge. And then you always want to tell them by what test. So by the nth term test. Okay. Next example. Oops, that should say n and n, because we are doing series, silly goose. Okay, so right away, I'm going to take the limit as n approaches infinity of the series. So 4n squared minus 5 over n squared plus 3. The powers match, so it's just going to be a ratio of the coefficients. So 4 over 1 is 4. say it's not equal to 0, so we're going to diverge by the nth term test. Okay? So if you could take the limit, it's not equal to 0, done. Nth term test for divergence. Honestly, these tests aren't in any specific order, but I'll go through which kind of my thought process when I'm doing a series at the end. All right, what do we got next? So we have the integral test. In order to use integral test, there is a little saying to remember what we need to state in order to use the integral test. So if you use the saying, "In prison, dogs curse," it kind of helps you figure out that, okay, in order to use the integral test, the P in prison, the terms must be positive, dogs decreasing, curse continuous. And you're going to use it if you can easily integrate, although I probably wouldn't use this very often because it's kind of lengthy. And the series is going to converge if the integral converges, and the series is going to diverge if the integral diverges. So let's go ahead and do that. Here we go. So we're going to integrate from 1 to infinity, 1 over x plus 1 dx. You want to turn it in terms of x to make it function notation. We know that that is an improper integral, so I'm actually going to finish it up here. So we're going to replace the problem's infinity, with b, and we're going to take the integral of this. All right, if you're unsure of what this is natural log. I can show you the u sub off to the side. So u is going to be x plus 1, du is dx, and then this is going to be 1 over u to u, which is the ln absolute value of u. So this is going to become the limit as b approaches infinity of the ln absolute value of x plus 1 from 1 to b. Okay, so now we're going to have the limit as b approaches infinity of the ln absolute value of b plus 1 minus the ln absolute value of 1 plus 1, which is 2. Well, if you know what the natural log graph looks like, which it looks like this, guys, and the ln of b plus 1 kind of just shifts it, the natural log graph is going to look like this. So no matter what, even if we're shifted to the left 1, we're still going to, as b is approaching infinity, this graph is going to infinity. So this is going to be divergent. So the integral is divergent. So the series diverges by the integral test. Okay? So like I said, this would kind of be a last resort one. Honestly, I don't know. I like the limit comparison test even better than this. So I would probably use the limit comparison test on this. But you do you. All right, this one is a great test, P series. So you're going to use it when the series looks like this, n to the p. Now here is something important. P is a constant. So we are going to converge if p is greater than 1, diverge if p is less than or equal to 1. All right, so what do we got here? Look at this first example. You can see here that p is equal to 3. So I'm going to say p is equal to 3. P is greater than 1, so we converge by the P series test. Okay, I think they're very easy to spot. Look at this next example. So maybe at first glance you're like, how is that P series? Well, because you can turn this into a fractional exponent. So we're going to have n equals 1 to infinity, 1 over n to the power of 1/3. So P is 1/3, which we know is going to be less than or equal to 1. So we are going to diverge by P series. And now there's a special series called the harmonic series. It's a special case of the P series. So I'm going to write special case of P series. Special case. And you can use the harmonic series to compare series to when you're doing the direct comparison test or a limit comparison test. So this is what the harmonic series is going to be. N equals 1 to infinity, 1 over n. Okay? And you can see that it's going to diverge by the P series because look, see that little 1 right there? P is equal to 1. Well, if P is less than or equal to 1, we diverge by the P series. Okay, so the harmonic series, which is right here, is always going to diverge. It's a special P series. All right, next, number 5, the alternating series test. I think the alternating series test is one of the easier ones to spot. Whether or not it's easy to use, that's up to you. So let's look here at this one. The alternating series test will only test for convergence. I should write that down. Can only test for convergence, not divergence, okay? Not divergence. And it's easy to spot because it's going to have some sort of multiple in front of the series that implies that it's alternating. So -1 to the n, -1 to the n minus 1, -1 to the n plus 1, and so forth. I'm actually going to make that like that. Okay. So, yeah, sure, it doesn't matter. Your goal is to figure out, first of all, what is attached to the alternating piece. And we're going to want to identify B sub n, which you'll see in a minute. And here are the conditions. We're going to converge if, and I make my kids do it in a specific order. First, I make them take the limit of B sub n as that approaches infinity and make sure it's 0. If we pass that, we can move on to the next step, which says B sub n plus 1 has to be less than B sub n, because what we're doing is we're showing that it's going to be decreasing, okay? So if you look at this first example over here, if I write it like this, it's easier usually for you guys to see. So B sub n is what is attached to the alternating part. So I'm going to start by identifying that B sub n is 1 over n squared. So step 1, we're going to show the limit as n approaches infinity of what we just said B sub n is. So common mistake is we look at this and we say, oh, this converges by P series. You're right, but that's not the correct conditions for the alternating series test. We need to show that the limit as n approaches infinity of B sub n is equal to 0. It is. The denominator is going to grow faster than the numerator. Check. Next step. Then we need to say 1 over plus 1 squared. It's B sub n plus 1, so that means we're going to, everywhere we see an n, we're going to replace it with n plus 1, is less than 1 over n squared. And you can kind of reason that out. That is, in fact, true, because let's just think together. Let's say, like, n is equal to 2. If we let n is equal to 2, let me move this down just a little bit. If we let n be 2 right now, this would be 3 squared, which is 9. And then if we let n equal 2 here, that would be 1/4. Well, 1/9 is less than 1/4. So now we can say we converge by the AST, alternating series test. All right, next example. This one's great because they already, B sub n's right there. It's what's being multiplied. So step 1, if I were you, is I would write down what B sub n is off to the side. Now let's take the limit as n approaches infinity of B sub n and make sure it's equal to 0. Well, it's not. It's equal to 1. So it's not equal to 0. We cannot say we are divergent by the nth term test. So when this happens, we are going to say we diverge. Sorry, did I just say? We can't say we are divergent by the AST. I got ahead of myself there. So back it up here. Back it up here, Cola. So if we take the limit as n approaches infinity of this, we see that it's equal to 1. That's bad. I want it to equal 0. It doesn't equal 0. We cannot say we diverge by the AST. We have to jump and say we diverge by the nth term test. Because what does the nth term test say? As long as we get a limit not equal to 0, we are going to diverge. And you might be wondering, well, like, why? Well, if you look at this series that I'm going to highlight all in purple, this series is going to continue to oscillate, okay? It's going to keep jumping -1, 1, -1, 1, blah, blah, blah. So we're going to diverge by the nth term test. So if we, that's an important thing to note. If we fail the AST, say we diverge by nth term test. Okay, next, LCT, which we know stands for limit comparison test. I don't know, I like the limit comparison test. You can use the direct comparison test as well, but I teach it with the limit comparison test. So you can easily use this. You can use it if you can easily compare the series to a geometric series or a P series. So you're going to see what I mean. So what you're going to do is we're going to choose a B sub n that is going to behave very similar to the series that I gave you. Then you're going to take the limit of a sub n over b sub n and make sure you get an answer, L, that it's greater than 0. And if b sub n converges, then a sub n will. If b sub n diverges, then a sub n will diverge. So check this out here. And the way I say to pick what b sub n is we kind of look at our dominating terms. So up top, the dominating term is going to be 2n. You're essentially looking at the term with the higher power. If you sat here and FOILed this out, the dominating term on the bottom would be n squared. So now I'm going to write my dominating terms. Ready? B sub n is going to be 2n over n squared, which is 2 over n. So now what I'm going to do is I'm going to take the limit as n approaches infinity of the original series over b sub n, which is times the reciprocal of b sub n. If we do this, the higher power on top is going to be 2n squared. If I sat there and FOILed this out, this would become, and sometimes it's nice for me to show you the algebra. Like down here, if I actually squared this out, it would be n squared plus 2n plus 1. If I pull the 2 in, the denominator would be this. So the higher power on top is 2n squared. The higher power on the bottom is 2n squared. So this limit is going to be 1, which is greater than 0. So the limit exists. So now we have to go and say, what does b sub n do? Well, look at b sub n. B sub n is 2 over n. That is a multiple of the harmonic series. So b sub n is going to diverge by harmonic series. So because the limit exists and b sub n diverged, then a sub n is going to diverge by the limit comparison test. Okay? All right, look at this example. So here we go. First things first, let's look at the dominating term up top. It's just 1, and the dominating term on the bottom is 2n. So b sub n is going to be 1 over 2 to the n. All right, next, let's take the limit as n approaches infinity of the original times the reciprocal of b sub n. If we take this limit, it's going to be 1. Okay, great. So now we have to figure out what b sub n does. So b sub n is a geometric series because, guys, watch. I can turn this into 1 over 2 to the n because if you broke this down to be 1 to the n over 2 to the n, 1 to the n is always going to be 1. So I don't need to write that. So because it's a geometric series, we're going to look at r, and we're going to say, so let's do it. Let's say, I'll do it in another color. R equals 1/2. The absolute value of r is less than 1. So we are going to converge by the geometric series test. So a sub n converges by the LCT. Because remember, whatever b sub n does, a sub n does, as long as we show that the limit equals a number greater than 0. All right, the ratio test. I don't know why. If I had to pick a favorite, it would be this one. Let's highlight it so it matches everything. I think I used purple. So the ratio test, the kind of dead giveaway to use the ratio test is there's going to be a factorial. And we're going to converge if the absolute value of a sub n plus 1 over a sub n is less than 1. And we're going to diverge if we're greater than 1. So let's do it. I don't know. I just love this test. So let's take the limit. Let's also move it down. I need some space because of the way I like to do it. As n approaches infinity, the absolute value. So everywhere we see an n, we're going to replace it with n plus 1 times the reciprocal of the original. And now we're going to break some things down. But I think it's important for me to show you how I break down n plus 1 factorial. So if I did 8 factorial, that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But maybe I don't want to write it like that. What I can do is I can pull out the first term and kind of collapse the remaining terms and make them their own factorial. So what I'm highlighting in purple here could actually be written as 7 factorial. So 8 factorial, if I wanted to, I can break it down to 8 times 7 factorial. Same thing here. Check this out. N plus 1 factorial. Factorial means keep decreasing the terms by 1. So the next term would be n, then n minus 1, then n minus 2, and so forth. But instead of writing it like this, take the first term and then just tack a factorial onto it, because what I highlighted in purple is equivalent to n factorial. So n plus 1 factorial could be broken down to n plus 1 times n factorial. 8 to the n can be broken down 8 to the n times 8. And now I like to cross off things that repeat. So let's use a different color that's like kind of going to stand out, black. N factorial, goodbye. 8 to the n, goodbye. So now what are we left with? Let's write what we are left with. We are left with the limit as n approaches infinity, 8 over n plus 1. Well, if you take that limit, it is equal to 0, which is less than 1. So we're going to converge by the ratio test. Okay, let's do another one. So come over here. So step 1, take the limit as n approaches infinity of the absolute value of the nth plus 1 term. So if I do that, that's n plus 2 factorial times the reciprocal of the original. Let's break some things down. So this is 2 to the n times 2. And this is n plus 1. Take out the first term and then throw a factorial on the rest. So what can we cross out? The n plus 1 factorials and the 2 to the n. So we are left with the limit as n approaches infinity. It looks like 2 over n plus 2. Well, that limit's equal to 0, less than 1, converge by the ratio test. Isn't that fun? I don't know. It's like a little puzzle. And then last but not least, if they ask us if we are absolutely or conditionally convergent, so here we go. We are going to be absolutely convergent if the absolute value of the series converges, because that means we're going to converge absolutely all the time. And we are going to be something called conditionally convergent if the absolute value diverges, but the original series converges. So you're going to watch me do this here. So this first one right here, what we're going to do is we're going to take the absolute value of this series. So if I take the absolute value of this, so I absolute value this, you're going to be left with n equals 1 to infinity, 1 over n. So now you're going to see what this one does. Does this converge, diverge? Use one of the tests that I taught you. Well, this is the divergent harmonic series. Okay, so because the absolute value of the series diverges, now we need to test the original series. So the original series is an alternating series. If I write it like this, it should help you guys. Negative 1 to the n times 1 over n. So now I'm going to go ahead and we're going to test the original. So step 1, we're using the alternating series. Guys, this always happens, okay? So if the absolute value diverges, you're going to test the original, which is an alternating series. So step 1, we need to identify b sub n. It's what's attached to the negative 1. We're going to take the limit of that as n approaches infinity. Make sure we get 0. We do. And now next step is we're going to want to show that we are decreasing. So we're going to show that 1 over n plus 1 is going to be less than 1 over n, which is true. So we're going to converge by the AST, which means we are conditionally convergent. Conditionally convergent. Okay, let's look at one more. So first of all, let's take the absolute value of a sub n. It's going to be 1 over n squared. Well, that's the p series. P is equal to 2. So when p is greater than 1, we are going to converge by the p-series. So because the absolute value of the series converges, donezo, we are absolutely convergent. Oops. Okay, that's it for the series test. So now I'll make another video shortly on the remainder of Unit 10, which is a wonderful unit. Have a good day.